Alright, so welcome to Separable Forces, Physics 360, Chapter 4, Section 3. So let's get started. So what is a separable force? Well, a separable force is a force that each coordinate or axis that the force lies along is independent of the other coordinate. So that's a separable force for Cartesian. This would be a separable force for that spherical, and this would be a separable force for cylindrical coordinates. What is not a separable force is something like this. In this case, the x component of the force depends on z, and the y component of the force depends on x, and the z component of the force depends on y. That is not a separable force. Same way with this one, the rho coordinate depends on z, and the phi coordinate depends on rho, and the r coordinate depends on z. I don't think that should be r right here. I don't think this right here should not be r. That should be phi or rho. Probably it should be rho. Okay, sorry about that. So we're moving on. All right. Okay, more on separable forces. So let's say we have this force. What other quantities will this force have? Well, earlier in conservative forces, we found if we took the curl of F, which is this thing, and if it equals 0, then the force was conservative or internal to the system. So how do we take the curl? Well, using Kramer's rule, I cross out the I, and that leaves me with these two. So if I multiply the in the way of the blue arrows, I get the I coordinate is this, and the second arrow, the ones that are going up, are always negative. And I do the same thing for the J arrow. So that's the second element, so there needs to be a negative sign in front of that. And so doing the same thing, I get this, and then I do the same for the Z, and I get this expression. Well, you'll find out here if the force is separable, if you look at the x coordinate. See, this is just a function of z, but the velocity, the derivative with respect to y. And since there's no y's in here, this is a constant, so that's 0. And over this one, there's just y's with respect to z, so that's 0. So we take the derivative of this. Again, this will be 0, this one will be 0, this one will be 0, and this one will be 0. So basically what this says, if we have a separable force, then the curl of that force is always equal to 0, or a separable force is a conservative force, or has forces that are internal to the system. So that should be, now, it's not the opposite. If a force is conservative, it may not be a separable force. But this says if the force is a separable force, it is also a conservative force. Alright, so example, projectile motion is that, and then if we write out the force on a projectile, we get this, and we're assuming no drag in this case. So what I do is I know that the change in momentum in the x direction and the change in momentum in the y direction are 0, and I get the change in momentum in the z direction is this, and so then we're trying to just predict the velocity of this object. So I'll change the momentums into velocities, and we'll divide by the mass, and we get this expression for the derivative of the velocity of each coordinate and with respect to time is equal to this. Well, we can solve this. Those two are quite straightforward. We know that the x velocity has to be constant and the y velocity has to be constant. And then if you solve the other one, you'll find out, you'll get this, where c is another constant, depending on the initial conditions of the system. So if we claim we fire a projectile at some angle theta with some initial velocity v0, it's going to have an x component of the velocity equal to that, and a y component will be 0 because we're going not going into the y direction. And the z component would be this. And then, so we get this is the velocity, or what describes the velocity as it changes in time. Now, if we wanted to get the position, we would use the definition that the change in position with respect to time is equal to the velocity, and we do a similar thing for each coordinate, and then figure out what the positions of this object over time. But this is one example of a separable force. And I'll see you in class. Bye.